this video, we will be talking about gas laws. In particular, we will be discussing the ideal gas law, which is the only gas law you really need to remember for this course. Memorize it. If you do, it will make your life much easier. Before we get into gas laws, let's review gases. Gases are characterized by having no definite volume. They will expand to fill their container. They also have no definite shape, and they'll take the shape of whatever container you put them in. Gases are mostly empty space. The particles are very far apart, and they're not in direct contact with each other. Particles move randomly, changing directions only when they bounce off the sides of the container or bounce against other particles. Gas particles exert pressure as they bounce off the walls of the containers that they're in. Now, pressure is defined as force per unit area. The collisions of the particles supply the force, and the wall of the container supplies the area. Gas exerts pressure in all directions. Predicting how a gas will behave is a little tricky, since in order to do this, you'd have to take into account things like how much space each gas particle takes up and the tiny intramolecular forces that can happen between gas particles, especially at low volumes and low temperatures. So when we use equations to predict the behavior of gases, we tend to use ideal gases as our model or approximation. Now, what are ideal gases? Ideal gases are defined as a gas in which there are no intermolecular forces between the particles. All collisions are elastic, which means if particles bounce off of each other or off of the wall, no kinetic energy is converted into any other type of energy like heat. The gas particles also take up no volume and are infinitesimally small. Although there's really no such thing as a gas that actually behaves this way, because gas particles do take up space and they do exhibit intermolecular forces. Many real gases behave more or less like real gases under standard conditions. So this is not a bad approximation for these gases. Now we're ready to talk about the ideal gas law. The ideal gas law combines a bunch of smaller gas laws that were discovered in the 1700s and the 1800s. You may have run across some of these gas laws before. They include Charles' law, Boyle's law, Gay-Lussac's law, Avogadro's law, and the combined gas law. If you have time for some history, there's some great science that went into discovering these relationships. But if you're strapped for time, know that all of these laws can be derived by using this one magical equation and a little bit of algebraic manipulation. And I suggest you learn how to do this since it will make your life much easier. Here is the ideal gas law. PV equals Nrt, where P stands for pressure, V stands for volume, N equals the number of moles of gas particles. And it doesn't matter what these particles are. T equals temperature, which must be in Kelvin, or you will get the wrong answer. R is a constant that's on the AP formula sheet. It comes in several different versions, and you pick the one with the units that match the ones that you are using. So check your units, then pick the constant that matches. Now let's look more closely at the relationships between the various variables in this equation. If you look closely at this equation, you'll see that pressure and volume are inversely proportional. If we hold N and T constant, we see that as the pressure goes up, the volume goes down. If you look at this relationship on a graph, you will see this inverse relationship. As pressure increases, volume decreases, and vice versa. Now, let's use this PhET simulation to explore this further. If we increase the volume, we see that the pressure must decrease in order to hold the number of moles and the temperature constant. If we decrease the volume, we see that the pressure increases. It works the other way too. Increase the pressure and the volume will decrease. Decrease the pressure and we see that the volume increases. Now let's focus on what's happening at the particulate level. Since the temperature is constant, the speed of the molecules will stay the same. Since the number of moles is constant, N will not change. As we decrease the volume, the size of the wall of the container shrinks a little bit. There's less area for these particles to bump against, and there are more particles hitting each unit of area. This is what pressure is, force per unit area, and this is why the pressure goes up. Now, if you increase the volume, there are fewer particles hitting the wall per unit area, and the pressure goes down. Here's another way to look at this. Using a little algebraic manipulation, we can derive Boyle's law, which looks like this. This is Robert Boyle, and he came up with this law in 1662. We care about this because we're going to see problems like this one from ck12.org. Now, I could just memorize and use Boyle's law, or I could derive it from PV equals nRT, and this is a lot easier to do. Let's start with PV equals nRT. Now we have our initial situation, which we're going to give us subscript 1, 2, and we have our final situation, which we will denote with a subscript 2. Now, nRT, they don't change. So we are going to set these equal to each other, and we get Boyle's law. P1V1 equals P2V2. A sample of oxygen has a volume of 425 milliliters when the pressure is equal to 387 kilopascal. The gas is allowed to expand into a 1.75 liter container. Calculate the new pressure of gas. So we're going to need to list the known quantities, and we also want to plan our problem. We know that the initial pressure is equal to 387 kilopascals. We'll denote that as P1. We know the initial volume is 425 milliliters, and we know that the final volume is 1.75 liters. Now, we're going to have to change these so that the volume is in the same units, and I'm just going to change my 1.75 liters to 1750 milliliters. Now, I could translate V1 to liters. Either one of them would work out. My unknown is the final pressure, which is going to be P2, and I know that's going to be in kilopascals. Now, when I solve equations like this, I like to rearrange my equations algebraically so that what I want to solve for is on the left. And I've done that here. I want to solve for P2, and so I've rearranged the equation so that P2 equals P1 times V1 divided by V2. Now it's just a matter of plugging my numbers in, and my answer is 94.0 kilopascals. Now let's look at the relationship between volume and temperature. We'll assume that we're holding the number of moles and the pressure constant. From the ideal gas law equation, we see that volume and temperature are directly proportional. If we hold pressure and the number of moles constant, and if we change the volume, the temperature goes up. If we change the temperature, the volume will go up proportionately. We have a linear relationship. We can see this in this PhET lab. Increase the temperature, and the volume increases. Decrease the temperature, and the volume decreases. With a little algebraic manipulation, we can take the ideal gas law and derive Charles's law, which was proposed by Jacques Charles in 1787. We're going to hold P and N constant, and R is a constant anyway. I'm going to give my initial conditions the subscript 1 and my final conditions the subscript 2. P, N, and R do not change, and I am going to rearrange so that I have the variables I want to solve for on the left-hand side of the equation and the ones that remain constant on the right side. Since V1 divided by T1 equals NR over P, and V2 divided by T2 equals NR over P, I can use substitution and derive this equation, which is Charles's law. Though it seems pretty complicated at first, it can become second nature if you just practice, practice, practice. Now let's show this in action. We're going to calculate the decrease in temperature when 2 liters at 21 degrees Celsius is compressed to 1 liter. So we're given that our initial volume, which we'll designate as V sub 1, is 2.00 liters. Our initial temperature, T sub 1, is 21.0 degrees Celsius, and our final volume will be 1.00 liters. Notice that our initial temperature is in Celsius. When you are working with gas laws, you cannot use Celsius, and you must translate temperature into Kelvin. This conversion formula is on your AP chemistry formula sheet, so you might want to find it so you know where it is. So I will convert Celsius to Kelvin, and I get 294.0 Kelvin. I can use algebraic manipulation to rewrite PV equals nRT into the form of Charles's law. I'm going to rearrange my equation to solve for T. You don't have to do this, but I find that sometimes it's easier to deal with units if you do it this way. I'm going to plug in my numbers, and my final temperature is 147 K. Let's take a look at the relationship between pressure and temperature if we hold our volume constant. As you can see from the ideal gas law, pressure and temperature are directly proportional. That means they are linearly related. If we increase one, the other has to increase as well. We can see this using our PhET simulation. Let's set volume and the number of moles constant. Crank up the temperature, and we see that the pressure goes up. If we decrease the temperature, we see that the pressure goes down. We can easily rearrange PV equals nRT to derive the equation proposed by Gay-Lussac in 1808, otherwise known as Gay-Lussac's law. We're going to hold volume and the number of moles constant, and R is a constant anyway. They don't change. We have our initial pressure and temperature, which I'm going to label P1 and T1, and then we have our final temperature and pressure, which I'll label T2 and P2. We are going to rearrange our equations like this, and we see that P1 over T1 equals nR over V, and P2 over T2 also equals nR over V. We are going to use substitution and derive Gay-Lussac's law. P1 over T1 equals P2 over T2. Now, if we're given a problem relating temperature and pressure, we can rearrange Gay-Lussac's law to solve for whatever variable we need. In this case, I've put T2 on the left, but we could rearrange it to solve for anything we want. What if we need to find the relationship between the number of moles and the volume? Now, we can see from our ideal gas law that if we keep the pressure and temperature constant, volume is directly proportional to the number of moles. This will be a linear relationship. In 1811, Avogadro proposed that equal volumes of gases under the same conditions of temperature and pressure contain equal numbers of molecules. Well, we can derive his equation from the ideal gas law. I'm going to start with PV equals nRT. P, R, and T are constant. They will not change. I'm using the 1 subscript for my initial conditions and my 2 subscript for my final conditions. I'm going to rearrange these equations so that the things that are changing are on the left and the things that are not are on the right. I'm going to use substitution to get Avogadro's law. V1 over N1 equals V2 over N2. And if I'm given a problem where I'm asked to relate the number of moles to the volume, I can rearrange this equation to solve for any variable I want. The implication of this law is that a volume of gas at a given temperature and pressure is going to be directly proportional to the number of moles of gas. It does not matter what the gas is. If you double the moles, you double the volume. Now, there are a couple numbers on the AP formula sheet that you're going to want to know. At standard temperature and pressure, which is 273.15 Kelvin and 1.0 atmospheres. 1 mole of an ideal gas will take up 22.4 liters. Remember that this conversion factor exists and know where to find it because it can be very useful when we are talking about gases. What if the pressure and the temperature and the volume all change? This is where the combined gas law comes in handy. This gas law combines Boyle's law, Charles's law, and Gay-Lussac's law, and it can really come in handy. We'll start with PV equals Nrt. We're going to be holding N and R constant. And I'm just going to do some algebraic manipulation to get all the things that are going to change on the left-hand side of my equation and leave Nr, the things that don't change, on the right-hand side of the equation. I'm using the subscript 1 to denote the initial conditions and the subscript 2 to denote the final conditions. I can use substitution to set these values equal to each other and get the combined gas law. P1V1 over T1 equals P2V2 over T2. And remember, anytime you use this equation or any other gas law with temperature in it, the temperature must always be in Kelvin, and you can find the conversion factor on the AP equations and constant sheet. In summary, we can use the ideal gas law to relate pressure, volume, the number of moles, and temperature to each other. R is a constant which we can look up in a table. Depending on which two variables we're looking at, we can use algebra to rearrange the ideal gas law to derive Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and the universal gas law. PV equals Nrt is one-stop shopping. Memorize it, use algebra to derive what you need, and practice, 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 and you'll be fine.